So now we are at the genus command prompt. So this tool runs on command prompt mainly, and we can only use the GUI to view the schematics and so on. So we're going to write commands to do synthesis, and we're going to type those commands here at the command prompt of this tool. So the commands are actually shown here in this script. So there are two ways to do it. One is you can just source this entire tickle file, or you can type in one command after the other at that command prompt. I have also written comments here in this file to help you do all the steps on your own. So to understand this better, let us first do it one command after the other. First, let us understand the commands. The first command here is to set the library paths. That's the first step. So we're going to use this command, set attribute init underscore lib search path. And this is going to search the libraries in the path that you provide here. So all of this is with respect to the folder from which you have launched the tool, and also the folder from which in which you find the script, the tickle script. So therefore, it says one level up, and then you have the lib. So this is where the library files are present. That's what it means. So it's telling the tool to search for the library files in this path. And there are multiple files here. So which one of this is it going to use? So it is we have to specify that as part of this command here, and we are asking it to use the slow library. So let us first understand what this library file means. So this is provided by the vendor, or it's coming along with the PDK. So whoever is going to fabricate this, that fab is going to provide this lib file. So this is the library for the slow corner. And here it's going to contain initially some units of time, units of capacitance, current, power, voltage, and so on. And later on, it's actually going to start containing the cell names. So I'll search for a cell name here. Let me search for inverter X1. So I know this command, this cell exists. So let me search for inverter X1. So this is a cell. It's an inverter. It's going to contain the area of that inverter, the VDD, the name of the VDD pin, the name of the VSS pin, what is the leakage power of this particular inverter. And it's also going to contain what are the pins it has, or the ports it has. So this is an output port. And what is the functionality of this? It is going to do negation of the input A. And it also contains a lot of timing information with respect to that input pin. So it has the rise delay, the rise transition. Then it also has the fall delay, fall transitions, etc. So basically, it also contains the power information with respect to the input. And then it starts the input direction, that is A is the input. And then it also contains the capacitance associated with the input and so on. And similarly, it moves now to the next cell, and so on it goes up to all the cells, up to the point it covers all the cells that are in this library. So it's arranged in alphabetical order, and the last one you should be able to find is an XOR gate. So inverter X1, X2, X3 usually means it's of course single input, single output, but it's going to have different sizes. If it's an AND gate, it might be of multiple inputs, different number of inputs, different sizes, and so on. So that is how you have different cells in the library. So now you should make sure that you do not change anything or edit anything here. Otherwise, you will end up getting wrong results or wrong timing information. So that is the first step. You have to provide the path to the library and also specify which of the libraries you would like to use. Then you also have to specify which path to search for the RTL. So we have specified this folder called RTL, and we have our RTL inside this. So this is a simple counter which is just counting up. It's a behavioral Verilog code. Make sure that it's a Verilog code or a VHDL code and not anything else. So, and which design do we want to synthesize is specified as part of read HDL, that is the next command. And we're going to use the counter.v. So we're going to read that netlist here. So these are the important inputs here. We specified the library, we specified the file that we want to synthesize. So now another input is going to be the constraints, which we will do at this point in time. So before that, we can do this step called elaborate, which basically connects all the modules if there are any undefined modules. And if you have written that as part of separate files, it's going to connect it. And that's the elaborate step. Then at this point, you can also use this GUI underscore show. So it will open up the GUI for this particular tool. And I've also written commands here on what steps you can follow in when you open the schematic. So you can click on, I'll show this later on. So you can expand the schematics and also view the design in schematic. And then make sure that you hide the GUI and do not exit it, because if you exit, it will exit the entire tool. So now the next thing that we're going to read is read the constraints. So let us read the constraints here. So the path for that is again has to be specified with respect to the path in which this script exists. So if we open this STC file, it's called .stc. So we've created a clock, given it a name, which is the same name as the clock in the counter, which has a period 1 nanosecond. So it's all nanoseconds. And this is 0.5 is the half period. So it is basically a duty cycle of 50. And the port that you're going to assign to this clock is the CLK in our counter. So the counter has a CLK clock, and that's what we're going to use as the port here, port name here. And then we are setting the clock transition, which is the rise time. So this is 0.05, which is 50 picoseconds of rise time for the clock, and again 50 picoseconds of fall time for the clock. We set a 10 picoseconds of uncertainty for the clock, and then we set an input delay. So this is just been set randomly. You can try to change this and see what happens to the timing. I've set a small input delay of 50 picoseconds for the reset with respect to the clock. Similarly, an output delay for the count with respect to the clock. So this is all syntax. So the rest of it, if you simulate this for, or if you synthesize this for a different design, you'll have to change these names, and also you can change these numbers if you want a different frequency and so on. So that is the constraint file, and we read the constraint file here. So by this step, we are actually done reading all the inputs that we need for synthesis. So the next step is to actually synthesize it. So for that, the first step is, there are basically 3 commands. The first command for synthesis is syn generic. You can also call it syngen. So this is going to synthesize the design to generic gates. So synthesize meaning it's going to convert our counter to a set of logic gates, or in other words, it's going to convert this into a structural design, into a structural Verilog, using the library cells that exist in this file. So it can use only the cells that exist here. But of course, in the first step, which is syngen, it is going to map it to a set of generic gates. It's actually not yet mapping it to this technology file. It will do that later. It is just mapping it into a set of generic gates. And there are different effort levels that you can set here. So effort level low means that it is uh, not going to optimize much, and it's going to uh, optimize it later on if you specify the effort level to be high. So typically put the effort level to high or medium so that you get a good optimized layout. So then when you specify syn generic, it's actually going to synthesize the design to a set of generic gates. At this point also you can do GUI show. It will now show the schematic at this point in time. You can also use the suspend command. So if you are running the entire script at one time using this command source, then it is going to run all the commands from the first to the last at one go. So you will not know what happens after each step. So if you want to pause in between, then you can use the suspend. So you can stop here and observe the results and move on. So once you complete SynGen, the next thing to do is SynMap. So SynMap is going to map this set of generic gates to the cells that we described or we provided in this lib file. So if there are any gates which do not exist in this lib file, they are going to be converted to another set of cells. So basically this is the important step where you map the design to a set of library cells specific to your technology node. So that is SynMap. At this point, you can report various results. You can report, for example, report power is not needed. You can report gates, so it will tell you what are the gates it has used during synthesis and so on. Then the next step is to optimize it. So this is a key step. Again, you can set the effort level to high and do synopt. Synopt will optimize the design and try to reduce the area, and try and meet the constraints that you provided. So if you provided a very strict timing constraint, it is going to try and optimize it at this step and try to meet it. At this point also you can do report gates. So it is going to remove all unnecessary gates or gates which are repetitive and so on. So it is a good idea to report gates at this point and see what it is provided. So at this point, the next step is you've completed the synthesis. So the next step is to just report out all the results, check timing, check area, and so on. So we are doing report power here. So you can provide the path where you want to save it. It's a good idea to save all results in one folder. Also make sure you don't have any spaces here. So don't give any something like this. So always provide an underscore or don't give spaces in the folder names. You can also check design for timing errors. It will report if there are any errors in this file. Then you write out the HDL. So this is the important output. In fact, these two steps are important because we are writing out the synthesized netlist, which we will be using later on for placement if you wish, or you can also use the synthesized netlist for simulation. So anyway, the output of synthesis is basically the synthesized netlist. So that is an important output. In fact, that's the only important output. So you can provide the output path and also the name here. You also write out the constraints. So if the tool has made any changes or optimized the ports or optimized the paths, it is going to set out those constraints here. So this is also an important output. Then finally, you can write out the gates, report the area that it is used in the using the total area in the lib file. It is going to tell you how much area it is used. You can report power, timing. So timing is another important parameter. So we're going to later on see there are different ways of reporting timing. So you can report timing for all paths. You can report timing for multiple groups of paths, from all inputs to all outputs, from all sequential inputs to all sequential outputs. You can report only failing paths, only passing paths, and so on. Or you can report all the paths. So we're going to see all that, but this is an important output. And that is it. So this is just a repetitive command, so don't need this. So if you want to write out a new file like this, so how did I create this file? You can actually use this command called write template, and it is going to write out a simple template file for Genus. You can also write out this template for power optimization. So if you give this -power, it is going to give you a tickle file, which you can be used for optimizing power. Similarly, if you want to optimize area, optimize everything, or you want to just retime the whole circuit, there are different templates. So I have used a simple template here, and based on that, I have explained all of these commands in this file. So maybe let us now try and run this. Let me copy it. So I'm already at the genus command prompt. So I'm going to first set all the paths. So to set the paths here, it will give you some warnings, but you can ignore. You read the HDL. I'm doing command by command so that we know how it works. Then we elaborate it. So it is elaborated the design, and it's saying it is done elaborating the counter design and so on. Then we read the STC. It is read and it said successful 1, failed 0. So it is read each of these commands that you have in that STC file. Then let me do syngen. So it says done synthesizing, done optimizing, and so on.